of CosmoQuest Astro 101. All right, so I wanted to make today actually a fun Astro 101 stream. And so I got to thinking about some things, and I was online and I was looking at physics games, and then I ran across a test for the physics GRE. And I just remembered how much fun it was prepping for that test. So I figured that we kind of like do a little quick study session, as a means of just having fun with physics and talking about the science behind it. I figured that I would probably just go like through the first like 10 questions. So there are 100 questions on this test, and the questions, they do get harder as you move to the higher numbered questions. So we're just gonna go through the first 10, and I guess how I want to do this is I'll present the question, and you guys will give suggestions on what the solution is. It's typically like five. There's five answers to each question, five possible answers to each question, and of course, only one of them is correct. And so, and then of course we could talk about the science behind it. There's something to do that's fun, and the reason why I'm doing this also is because of the fact that I now also have a iPad tablet, and I want to see if I can also use it to be able to like doodle the solutions and stuff like that. I just started playing around with it, so I don't know how this is going to really work out. But at the very least, we can talk about the science. So let me go ahead and quickly make sure I have all the comments. Hey, Side MT. I'm happy to hear that, Paranor. Um, yeah, I mean, I've never done it myself, and I want to try this, Hanny. So let's see how this works. So I'm going to go ahead and scroll down into the test. As you can see here, there's a table of information. I swear to you guys, when I first took this test, and I only took it once. Luckily, I only had to take it once um, to get into grad school, and it was a nightmare. I got to the test, and at first everything was cool. Well, this particular page gives you all the constants you may want to use for any sort of calculations you're making. Um, and honestly, I used this page for some of the calculations, but in general, my approach was to try to get through all the easy questions first. That did not require any sort of calculations. It was all conceptual. You could just kind of think through it and quickly give a good quick answer. But for some of the harder questions, they required some calculations. The ones that like you have to give a physical like value for the answer. But yeah, when I took this test a very very long time ago, it was a nightmare. Um, and they were very strict about the rules. In fact, if I'm not mistaken, one of the students that was taking the test was excused midway during the test because of something. I think they were talking or something like that, and one of the people that was supervising the test just came by and was like, "Give me your test," and everyone just stopped for a moment to look up, and we really felt bad because like that test costs a lot of money, at least from like a student perspective. All right, so let's go ahead and do this. And I'm gonna try to see if I can get things working with this tablet. As you can see right now, the tablet's mirroring. Let's see if I can make that a little bit better. The tablet is mirroring what's happening on my computer screen. And so I want to see if I get this working though. But we're gonna go through the first question. All right, and hopefully you guys can see things just fine. If you can't, let me know, and I'll like do a zoom in or something. All right. So the very first question, and they typically start off easy. Make sure I can get the whole question there. All right. First question: a ball is thrown out of a passenger window of a car moving in to the right. So we can ignore air resistance. Cool. If the ball is thrown out perpendicular to the velocity of the car, which of the following best depicts the path? Hey Guido. Which of the following best depicts the path the ball takes as viewed from above? So as we can see in all the images for the different possible solutions, the car is moving to the right. We have a person sitting in the passenger side of the car, on the passenger side of the car, and they throw a ball out, right? And so we can ignore air resistance in this situation. And so the question is, what path will the ball take once it's thrown out? There's 5 different possible solutions, though. What do you guys think? Let's see if I can. And while you guys are looking at that and giving possible solutions, I'm going to see if I can keep playing around with this and seeing if I can get it to work properly. All right, Handy, we got C. Handy, we have E. Excuse me. Tom, we have C. Checker Kev, we have B. All right. So I can tell from this that in this situation, so gravity is going to be acting in the direction that we're looking into the page, right? So for right now, we're going to ignore gravity. So we're going to ignore that axis. I would have to go with the solution for B. I'd have to go with the solution for B. And the reason being is this. While in the car, the ball is traveling at the same speed of the car, right? So unless there's a force to act on that ball, according to Newton's first law of motion, unless there's a force to act on that ball in the direction in which the car is moving, the ball is going to continue to maintain that velocity. Even once we let it go, it'll maintain that velocity. Now, the fact that we're throwing it out, and it says here perpendicular to the velocity of the car, the vectors for this, the fact that we're throwing out perpendicular from the car, and the fact that the car is moving at some velocity, in this case towards the right, I'm going to feel that the ball is going to end up traveling towards it's going to continue to have a velocity vector that's in the same direction as the car, and a velocity vector that's perpendicular to the car moving down towards the bottom of the page. So we're going to put that the first answer, and I'm going to record some of the answers here though, but I think it's B. I think the answer is B for this one. And if that doesn't make sense, let me know, and I'll try to re-explain it. Let's actually pull up like a note and maintain the answers. So, and yeah, I'm seeing that I've been trying to play around with the tablet, and it's not working out the way I want it to work out. So we're gonna make this work, but yeah, I can't use that right now. In fact, it's showing exactly everything I'm doing here. So continue. I'm opening up some notes here, and I'm just gonna make sure I record some of the solutions. So I'm thinking the answer is B, and I have a few here that I'll also record. Notes. All right, there we go. So of the possible ones, I'm seeing E, C, and B, and I'm just going to underline what I think to be the solution, which I think is B. So I'm with Checker Kev on this one. So E, C, and B. All right, so Henny asks, how would the ball go ahead of the car in B? Well, no, it's not indicating where the position of the ball is. It's indicating the direction of travel of the ball over some period of time. So, yeah, the ball won't be able to overtake the speed of the car. And given that we're ignoring air resistance, what you'd assume in this situation is that the ball would, if we could ignore air resistance and ignore the fact that gravity is going to pull the ball down to the ground, right? And works solely within the plane of this image here. What would end up happening is that the ball would have 2 velocity vectors. One velocity vector would be in the direction of the car, and the other velocity vector would be perpendicular to the car but pointing downward in the page. And so given those 2 velocity vectors, the resultant vector would have to be at a diagonal that is going towards the bottom right-hand portion of the page. Now, in all honesty, though, if you were thinking about this in 3 dimensions and you could still ignore air resistance, the ball would have a parabolic trajectory. So it would still kind of go in that direction, but it would fall down towards the ground in a parabolic trajectory. All right, so I got these possible solutions for the first problem, and thank you guys, for this is I love doing stuff like this, and so hopefully you guys find this interesting as well. All right, so moving on to the second question. Let's scroll that down so my face doesn't cover the question. I really want to get this working. All right, so number 2. An object is thrown horizontally from the open window of a building. Okay. If the initial speed of the object is 20 meters per second and it hits the ground 2 seconds later, from what height was it thrown? And so again, we have one of these situations where we can neglect air resistance and assume the ground is level. Now, honestly, for these first 2 questions, you can use a set of equations known as the kinematic equations of motion. And basically, they will allow you to define the motion of an object under the situation of constant acceleration. And so, given that we're able to ignore air resistance in these situations, the only acceleration acting on these objects would have to be gravity. And you'd have to, of course, think about these problems, well, for these situations, in primarily just in 2 dimensions. You can think of them in 2 dimensions. With the first one that I mentioned are in the plane of the page, and with this question, you can kind of have some vertical axis, which if you want to be the building, which is going to be, you could say, the z-axis, and it's being thrown out of a window, which if you want, you can name some x-axis. And so we could ignore the third axis because we'd imagine there's no motion in that along that axis direction. But yeah, getting back to number 2 though. Given what I've stated here, what do you guys think is the solution for number 2? So let me go back to the comments here. All right, Henny's saying D. Okay. I think I'm liking that. Yeah, I think I'm liking that answer. Can't remember the formula. All right, I'll tell you the formula. And this can work along any axis. I'm just going to put it in terms of change in x. The change in x, or the change in height in this case, is going to be equal to the initial velocity that the object has along that axis, or in this case along the z-axis, times time, plus 1/2 gt squared. Yeah, I think that's correct. Yeah, it gives you units of right. So if that's helping you any, 1/2 gt squared. You have to make sure that you also, like when you're doing these problems, you have to define a coordinate system. So we need to know whether or not the ground corresponds to 0 along the z-axis, and also you need to know which direction along the z-axis is positive and negative. All right, so great. So Henny and Checker Kev are both saying D, and you know what? I'm going to agree with D as well, based off of what I'm looking at here. And unfortunately, I can't work out the math on my iPad here. One of these days, I'm going to get this working now. But the idea here is that the change in height is equal to, in that first term, right, on the right hand side of the equation. I'm going to try my best to explain things here. The initial velocity in the z-axis, that is the axis that goes with the height of the building. Given that the object is thrown horizontally, there is no initial velocity along that direction, that up and down direction. Oh, wait. Wait a second. I think Checker Kev is trying to put the equation into the chat, and Nightbot just. Oh man. I wonder, is there any way we can like make Nightbot a little bit more relaxed on some of the comments here? But yeah, just to explain the equation really quick, no initial velocity along the z-axis. Therefore, the initial velocity times time is equal to 0, and you're only left with the term which is the 1/2 times gravity times time squared. Now we're given that the time is that it takes 2 seconds and you can actually use this. I mean, whenever you see people, like, for example, I've seen movies where people like in a cave and they'll take like a rock and they'll drop the rock, right? And allow the rock to fall and just count the amount of time that passes. They're able to take that information and determine how far down the bottom is. Exactly what Checker Kev said right there. So 1/2 times 9.8, where the 9.8 corresponds to the acceleration of gravity near the Earth's surface. 9.8 meters per second squared is the correct value for that acceleration. Times time squared, and the 2 corresponds to 2 seconds, so you have to square that. Sorry, no problem, no problem, Guido. Thank you though. And so when you do the math for that, you end up getting 19.6 meters. Now, on the test, when I was doing the GRE test, honestly, to make the math a lot easier, I would round numbers like that and just see which number was the closest. Um, so I would have probably did something like 1/2 times 10 times 2 squared, and 1/2 times 10 is 20. 20. Wait, 2 squared is 4. 4 times 10 is. Oh, wait a second. Hold on. That's 2 squared. Wait. The 2 squared is a 4. 4 times 10 is 40. And 40 divided by 1/2 is 20. So yeah, I would have gotten 20, right? And 20 is the closest answer to the 19.6. So that's how I would have went about trying to quickly solve the problem. Because honestly, when you're doing the test and you're trying to type things on a calculator, that could even take up time as well. So, but yeah, I agree with that one, and it seems like we're all in agreement that the answer for number 2 is D. So I'm going to quickly write that down as well. All right, so number 3. Make sure I have the comments up here. All right, so we're getting into some circuitry stuff. A resistor in a circuit dissipates energy at a rate of 1 watt. If the voltage across the resistor is doubled, what will be the new rate of energy dissipation? All right. So if I'm remembering correctly, I think that the equation for power is equal to the potential difference across your resistor times the current running through it. So P is equal to I times V. And we can convert that equation. So this is the equation for electrical power. If you have a current running through some sort of resistor and a potential drop across the resistor, the power that drops, the power that resistor uses or that load uses, is equal to the potential difference across it times the current running through it. But you can use Ohm's law to convert that equation in terms of voltage and resistance and their relationship to power. So to make a very long story short, though, I'd say that the power, the energy dissipation across our resistor, or P. All right, so Tom Van Scotter's already saying C. All right, I'm gonna mark that down. So you're saying 1 watt. P is equal to V squared over R. The voltage is doubled. So 2V quantity squared. So it's 4. So I think it's gonna be 4. I think you're gonna have 4 times as much power. So Checker Kev, so I wrote your answer down, Tom Van Scotter. So C. I'm seeing C right now. I think it's 4, guys. And the reason being, and again, I'm going to just try my best to explain it versus being able to write it down. Um, wait, Checker Kev is, yeah, so Checker Kev is using Ohm's law. V is equal to IR, where V is voltage, I is the current, and R is the resistance. Um, if V doubles, I doubles. So power equals V times I, so both V doubles and I doubles, so E. All right. So Checker Kev is also going with E, and I'm going with E too. All right, we're gonna. So the way in which I'm tracking the solutions is I'm writing down everyone's solution, but I'm writing the solution I think that is correct also at the very end of the line. You can't see what I'm writing here, but for the first one I have ECB, and I think B is the solution. Second one I have D, and I think D is the solution. And right now we have C and E, and I think E is the solution. All right, so I'm seeing. Let's see. Okay, so Tom Van Scott is asking why would the dissipation rate change? Um, because you've doubled the potential difference across it, and as Trekker Kev was saying there, if you've doubled the potential difference, you've also doubled the current essentially. So you're supplying more energy. If you can think of it like that, you're supplying more energy to the resistor. And so why wouldn't it burn out or something? All right, so in that situation, you're kind of getting into how much power can the resistor take before it fails. Good stuff, Trucker Kev. Um, so so mathematically speaking, um, the equation for the power that's gonna be dissipated through the resistor is the potential difference across the resistor, that quantity squared, divided by the resistance rating of that resistor. And so if you double the voltage V, you're getting the 2V and that being squared. And so the 2 squared makes 4. Right. So let's see. 3 is E. Right. Is that what yep, I got C and E. All right. So let's move on to the next question. Scroll down. Ooh, some more fun physics. Yeah, guys, I know this isn't all astronomy, and I'm pretty sure there's probably an astronomy question here somewhere. I'm not remembering exactly what the So this tests your knowledge on different areas of physics. Some of it's going to be quantum mechanics, some of it's going to be classical mechanics, some of it's going to be E&M, um, electricity and magnetism. Some of it's going to be astronomy. And so I'm pretty sure we're going to run into an astronomy question eventually. But of course, they don't do them in equal amounts. I think you're going to probably run into more E&M and more classical questions than any of the other categories I mentioned. So this one is definitely from E&M, given that I'm seeing that there's like a current and stuff like that. So let's go ahead and give it a try. Let's make sure that you guys can see things. All right, perfect. So I have number 4 states an infinitely long straight wire carrying current I I1 passes through the center of a circular loop of wire carrying current I2, as shown above. The long wire is perpendicular to the plane of the loop. Which of the following describes the magnetic force on the loop? Okay. All right, so I'm going to give you guys a few hints to this one. If I'm remembering correctly, you can use the right-hand rule for currents. So the idea is that you take your thumb on your right hand, because it's the right-hand rule, you take your thumb on your right hand and you point it in the direction of the current. And what ends up happening is the magnetic field that's being generated by that current will wrap around that current carrying wire in the direction that your right hand curls. So if the current's going up, in this situation, if I'm looking from above, the magnetic field should curl around that current carrying wire in a counterclockwise motion. Yeah, I had to look at that for a second there, guys. And you can do the exact same thing for the loop, right? If you wanted to, you take a single point on the loop, noting the direction of the current, and you just, for this situation, you'd simply just curl. And that would give you the direction in which the magnetic field lines are going in. And the other bit of information you'd want to be able to use is the magnetic force equation. There's two forms of it. The one for the current carrying wire, I typically never remember, but I can always just get it from the other version of it. F is equal to QV cross B, where F is the magnetic force. It's equal to the if you in this situation, if you have a charge traveling at some velocity v, as long as the velocity of the charge is perpendicular, well, as long as the charge has a velocity component that's perpendicular to the direction of the magnetic field, you'll produce a magnetic force on the charge. But you can convert that for current. QV, right? F is equal to I, the current, times the charge. Well, no. QV, Q over T, V length. Right. So I think it's I times L actually. Cross B. This is the reason why I would want to be able to write this stuff down. You can convert that QV term to having units, instead of having units of Q times V, you can have units of I times length. All I'm simply doing is taking the T in the bottom of the velocity variable, and I'm moving it underneath the Q. So Q over T is current, and what's left with the velocity is just the length unit up top. So current times length. And you can use that equation to work through this problem. And hopefully I have not confused you. And if I have, by all means, let me know. Like, Matt, bad explanation, re-explain, but better. And I'll do it. Oh, I'm seeing A. Okay. So yeah, you have to use the right-hand rule for this particular problem. For currents going through a wire. So I'm seeing everyone, wait. DC magnetic field. So I'm seeing A. And Checker Kev, are you saying E? So I'm going to write down A. So 4 is A so far. If I had to think about this really quickly. So if I'm looking at this right, the magnetic field that's being produced by current I1 is perpendicular. It's parallel. Sorry. It's parallel to the direction of current I2. And because it's parallel, with that whole cross product I was giving with the magnetic force equation, if you have two parallel vectors, the cross product between parallel vectors is going to be 0. So I'm going with E. Is that what you guys said too? Let's see. I've quickly forgotten. I'm going with E on this one. And to kind of explain it is because of the fact that the current I1's going up. its magnetic field is going to be perpendicular to the current I1's direction of travel. However, the field that's being produced by current I1 will end up being parallel to the direction of travel for I2. And so if you're looking at that whole cross product, the force on the current carrying wire for I2 is basically, if you can, I'll reduce it as being I cross B or I2 cross B. And they're parallel to one another, so the cross product must equal 0. So yeah, I think Trekker Kev was saying E as well. Or are you saying magnetic field E? DC, trick. DC, so no magnetic field. All right, no, you're saying E. Yeah, I'm with Trekker Kev on this one. So Hanny's asking, so it would be A if there were no current in the loop. Um, if there were no current in the loop that's carrying current I2, then there would be no magnetic force on the loop. And so Trekker Kev is stating here only AC generates fields. If I'm not mistaken, you would have to. I think you're correct on this one. I'm trying to remember. Right. Maxwell's equations, right? If you have a changing electrical field, then you can generate a changing magnetic field. Well, the charges themselves, that make up the current, each charge itself generates an electric field. However, to produce a magnetic field, though, you need you uh, you need for I think you need a time varying electric field produces a spatially varying magnetic field, and I think it's also vice versa. A time changing magnetic field will produce a spatially varying electric field. So yeah, I'm going with E on this one as well. I'm going with, and I want to see the answer for it too. Let's see. Let's go to the next one. All right, number 5. Um, De Broglie hypothesized that the linear momentum and wavelength of a free massive particle are related by which of the following constants? All right, guys, what do you guys think? This one just requires you to remember the equation or be able to derive the equation. And like I said before, many of the times when I was doing questions on the test, I couldn't remember all the equations. So I remembered a specific set of equations, and I could use those equations to derive the answers I wanted. And so on this one, I don't remember the exact equation, but I do know in general though what constant is going to be applicable to this problem. But let's see what you guys are thinking. All right, so Hanny, it's not E. All right, and E is yeah, it's not Avogadro's number, right? I agree with you on that. You'd use Avogadro's number. I remember using that like in chemistry and stuff like that. So it's like the number of particles per mole or something. So yeah, I wouldn't use Avogadro's number. Yeah, Avogadro's number can relate the number of particles per mole of substance. So what are you guys thinking? All right. So Checker Kev is going with B on 5. I'm gonna write down B. And let's see what everyone else is thinking. And so Hanny's going with B or C. Okay, B or C. All right, which one do you want to go with? This one I actually, this one I could just look at it and just know the answer. Okay, so B. On this one, I'm going to go with A. I'm going to go with Planck's constant. And my explanation behind this one is that the idea is this: you have you the so you're kind of getting into the situation of particle wave duality. Um, so with light, of course, we know that lights are photons are basically all waves, but they also at times exhibit particle-like features or properties. That is, they have momentum. And so, if you remember the equation, or not even remember the equation, I mean, if you've seen the equation before, E squared is equal to the rest mass of a particle squared um, plus its momentum times the speed of light, that quantity squared. I can't remember the name that would go with that equation, but this is the perfect equation to be able to examine the total energy of a particle. Um, and when you think of a photon, photons don't have mass. So you'd end up getting that the total energy of a particle, or the total energy of a photon, is equal to its momentum times the speed of light. Um, where this would be the energy of the particle, the energy of the photon is equal to its momentum times the speed of light. And so you might also remember there's another equation that relates that has a relationship with the energy of a photon, and that is the energy of a photon is equal to Planck's constant times the frequency of the light. And so you can actually equate the momentum that that a photon would have to its frequency. And so what you'd end up getting from there though is that the frequency is also related to wavelength as well. But you can make a relationship between the frequency and the momentum of the light through the momentum of the photon. Excuse me. I keep saying light, but I'm using light and photon interchangeably here. And so the long story short, and that's the reason why I wish I could write this stuff down right now. But long story short, you'd find that Planck's constant is what relates the two. So I'm going to go with A on this one. And guys, remember, if I'm saying something is not making sense, I can also even go online and kind of show you. I mean, you can look it up. You can look up the Broglie wavelength online, and it'll give the equation for it. But I just know that that's the relationship you'd use. Okay, let's move to the next one, guys. So number 6, talking about atoms. So we have an atom has field n equals 1, and it's n equals 2 orbital levels. How many electrons does the atom have? All right, what are you guys thinking? Out of the possible solutions, either 6 or 10. Okay. Tom Van Scotter says E. Oh, okay. I think I'm liking E. I think I'm liking E. This one could be tricky. You got to think about the periodic table of elements on this one. So, and you think about the periodic table of elements and think about what's the name of that last column? The noble gases. Noble gases. Um, and so this is actually something I learned in chemistry, and not so much in any of my physics courses. So you have to think about noble gases. So helium is a noble gas, and in its outermost shell, um, it has, or the n equals for the n equals 1. So also, if I'm remembering with the periodic table of elements, each n value corresponds to a given row, if I'm not mistaken. Um, so at the end of the n equals 1 row, the very first row of the periodic table elements, we have hydrogen, and then we have helium at the very end of that. And for helium, in its outermost shell, it has 2 electrons. At the very next row, the n equals 2 row, I think we start with lithium, and I used to remember this so well. I think lithium. I think eventually we would probably run into like boron, carbon, oxygen, nitrogen, and some other stuff. I think, but I can't remember exactly what's at the end of that row. But I do know though, at the end of that row, the outermost shell of that particular atom, if it's neutral, that is, it has 8 electrons. And so if you add the two from the two rows, the 2 electrons from n equals 1 and the 8 electrons from n equals 2 for those two noble gases, you should end up being able to you should end up being able to state that the total number of electrons would have to be 10. 2 from the n equals 1 and 8 from the n equals 2 orbitals. So I like E, and I'm gonna stick with E as well in this one. It's neon. Thank you. And in fact, I think you can also just look at the you can look at the, what do you call it, the atomic number for it. The atomic number would also give you the number of electrons, assuming, of course, that neon it's in a neutral state. None of its electrons have been ionized. That is. Good stuff. Good stuff, Hanny. I like that. All right. So I think we all agreed upon E for that one. All right. So number 7. Let's make sure you guys can see it as well, and my face is not blocking stuff. Let's see. Let's scroll down a little bit more. All right. So number 7. The root mean square speed of molecules of mass m in an ideal gas at temperature T is um what I'm thinking here is we can use the kinetic energy equation, which is 1/2 mv squared, and we can relate this to the thermal energy of the gas of particles. Um, I think that's going to be something like, for 3 degrees of freedom, I think it's three halves kT. And so you'd relate the one half mv squared to the three halves k 3/2 kT, and you'd solve for the velocity that's on the left hand side of the equation. And so, what are you guys thinking? I'm kind of, I didn't ask you guys, what are you guys thinking on this one? Yep, the 3 degrees of freedom are just 3 dimensions because the particles are able to travel in those 3 dimensions. It's always been and if I'm trying to remember if the situation is that, is rotation of the particles also considered um, a degree of freedom as well. Hmm. All right, so Tricker Kev is saying B for 7 because 1/2 only seems to go with 2, not 3 or 8. Do not need pi in D. So your guess is B. All right. So Tricker Kev's guess is B. That's our first guess. All right, so Hanny's going with C. All right. You know what? I think I'm going to have to go with Hanny on this. Because of the fact that there's 3 degrees of freedom, so that 3/2 kT, there's going to be that factor of 3 in the numerator on the right-hand side of the equation. And so I know the square root's going to have to definitely be there because it's v squared on the kinetic energy side. So I'm going to go with that too. I'm going to go with C on this one. I so pray right now that I am not boring everyone, and that this is that you guys are finding this okay. Honestly, sometimes I like to do this because I know if I like the saying goes, if you don't use it, you lose it. And so, every now and then I might just, like look see if there's like some physics trivia or some sort of science trivia somewhere. All right, so number 8. Number 8, the energy from electromagnetic waves in equilibrium in a cavity is used to melt ice. If the Kelvin temperature of the cavity is increased by a factor of 2, the mass of ice that can be melted in a fixed amount of time is increased by a factor of. Okay. What do you guys think? I need a quick moment to think about this one, actually. They're in equilibrium. All right, so Henny's going with C, and Trucker Kev is going with A. Okay, so let me write that down. So this is number 8. So I'm seeing an A and a C. I am so happy to hear that side, MT. Yeah, I love physics too. I mean, whenever I'm trying to explain it to my kids, um, I try to make it fun at times if I can, because they well, not so much they have very short attention spans, just that they're more like, I want to go play, and I'm like, let's sit down and talk about this for a second. What do you think? About this particular scenario, and I try to explain the physics behind it. They're like, you know what? That's boring. I want to go play right now. So let's see. And these are my thoughts on this one. So we have electromagnetic waves, and they're in equilibrium. I don't know. I'm thinking something probably like related to black body radiation, but I don't know if it's that. I do know that if you want to be able to melt ice, you start talking about the energy that's going to be deposited into the ice, and for that, you probably want to be able to know something about the specific heat capacity of the ice and stuff like that. Um, but it's the temperature. The temperature, though, is related to, in this situation, the temperatures have been increased because of something happening with the photons. Wait, time. The mass of ice that can be melted in a fixed amount of time is increased. So how does time factor into this? Energy and time, power. Okay. So maybe something with power here. And so how do I relate power in electromagnetic waves? The only thing that comes to mind is like the pointing. That's not it here though. Oh, wait. I think that this one is we can I think we can use Stefan Boltzmann's law for this. And so Stefan Boltzmann's law states but typically this is like like a power radiated from some source. It's going to be equal to the surface area that is covered by that power times sigma t to the fourth. And so in this situation, if I'm looking at the fact that it's the t is t to the fourth, and we increase the temperature by a factor of 2, um, 2 to the fourth power. I think D. At first, I was thinking something a little bit more linear. I was thinking about the fact for a black body spectrum for the max wavelength. You have a relationship between the max wavelength of that spectrum and the wavelength, or excuse me, the peak of that spectrum has a relationship such that the wavelength of the light times temperature is equal to a constant. But I don't think that's what we want to use here. I'm just gonna go with D for this one. Um, no, T to the fourth is not black body radiation. T to the fourth is Stefan Boltzmann's law. So Checker Kev is saying energy is equal to power times 2. Power times time. Okay. The only reason why I'm going with only reason why I'm going with this is that I'm thinking of the fact that they're incorporating time into this. Now I don't know if that's just information to kind of just throw me off, but okay, I'm gonna say that I don't know this one, um, and so I'm gonna go with I'm gonna be in between. I want to go with D as well, but I hear where you're coming from with the answer being 2. All right, so I'm just gonna say that I'm like in between those two answers, A and D on this one, but I think I think it's D. I don't know. Um, yeah, this is one particular one that I can't remember too well. But yeah, let's move on to the next one. I mean, right now we have A and we have D for this one. All right, so number 9. Oh, number 9 looks nice. I've seen this diagram before. All right, number 9. The figure above represents the orbit of a planet around a star. So here's one of the astronomy questions. I better get this one right. S. And the marks divide the orbit into 14 equal time intervals. All right. So basically, the time it takes to move from one point to another in the orbit is basically the orbital period divided by 14. If the only force acting on the planet is Newtonian gravitation, then true statements about the situation include which of the following. So in this situation, we can just apply Kepler's laws of planetary motion. And so number 1 says that area A is equal to area B, which is Kepler's second law, which I know is going to be correct. Number 2, oh wait, I'm just saying stuff right now. I want to hear what you guys thinking. Yeah, Kepler's law is right, Checker Kev. What are you guys thinking? What do you think of the answer, the solution for this one is? So yeah, equal area and equal time, right? That's right. That's correct, Hanny. But note that each tick, when you move from one tick to another tick in the orbit, you've done that in equal amount of time. So for the shaded area B, if you look at the orbit that corresponds to the shaded area B, we've moved from one tick to another tick. But for A, we've pretty much done the exact same thing. We've moved from one tick to another tick. So in the orbit, we've done equal time. Therefore, we must have equal area for the shaded areas. All right, so Checker Kev is saying E. All right, we have E. That's the first one. Any more? Any more possible solutions you guys think? All right. So are you saying C? Are you saying C, Hanny? Or are you saying that you're just sure about 1 and 2. All right. So Haney's going with C. So for this one, I know that all of Kepler's laws should apply for this system. Um, and so number 1, area A is equal to area B, is just the application of Kepler's second law. Number 2, the star S is at one focus of an elliptically shaped orbit. That's just the application of Kepler's first law. And then the third one, T squared is equal to C times A cubed, where A is the semi-major axis, and T is going to be the orbital period. This is Kepler's third law that relates the orbital period of a planet. Excuse me, the orbital period of a planetary body squared is going to be equal to or proportional to the semi-major axis of the orbit cubed. And so I'm going to also go with E on this one as well. Because given the conditions for this system, I would have to say that E is the solution for this problem. Okay, you don't know about so 3 is and I think we've had a conversation about this in the past. When we're looking at like exoplanets, or I think it was a discussion on exoplanets, and we were trying to see if we could use the exoplanet data to see if Kepler's third law is correct. And so what you'll end up finding is that the orbital period, and you can look at our planets in our system as well, and you'll end up finding that the orbital period of any of the planets in our system squared is going to be equal to, is going to be roughly equal to their orbital separation from the sun. Yep, that's right, Chikakev. You can change you can always change the proportionality by using a constant. In this case, they use a constant C. All right, so I'm going to go with E on that one. All right. All right, there's 12 problems on this page, and I'm seeing we're close to 130, so we're going to just quickly finish these up and, yeah, see what we end up getting. So number 10, a massless, actually there's like 3 minutes left, and I don't know how long this will take me to actually go through. And this is actually, the other ones are quantum mechanics. 11 and 12 are quantum mechanics. Yeah, we're getting close to 130, so I'm going to finish up here. A massless spring with force constant K launches a ball of mass M. In order for the ball to reach a speed v, by what displacement s should the spring be compressed? All right, so what do you guys think? Clue. You would probably want to relate the potential energy in the spring to the kinetic energy that the ball would be able to have once the spring's released. So you have like a mass on a spring. If you compress the spring, you're now giving the mass potential energy. And if you know the potential energy equation for a spring, you'd equate that to the kinetic energy the mass would end up having once you release the spring. Yeah, you're right. Not gonna finish in 3 minutes. Yeah, we're gonna end with number 10. I'm thinking I'm thinking so we're looking for displacement s. So I know the equation is gonna be one half k s squared in this case, where k is the force constant. It's equal to 1/2 mv squared. The 1/2s drop out on both sides of the equation. We're looking for s. We're going to have m over k. So whatever equation we're looking at, we need to look at m over k, and we're going to have a square root of m over k. And the only one that yep, Professor Melko, welcome. I'm going to have to definitely go with B as well. I'm going to have to go with B on this one. And so, all right, that ends it. I mean, right now we're gonna stop at number 10, and now we're gonna check our solutions. So I've written down all the answers that we gave, um, and the ones I've decided that I think is correct, I've put that solution towards the end of each line here. So let's go ahead and scroll down. There's a lot of good problems in here. We might do this again at some point in the future. But really, I wanted to do this because I wanted to be able to use my iPad and see if I could doodle some stuff on it during the stream. I've seen Pamela do it in the past, but I don't know how to do it quite yet. So let's go ahead and go to the bottom, see what's going on down here. By the way, this is what the test looks like. All right. And here we go. These are the answers. Except that, of course, on the actual test, you're not given the answers. Let's see. So I'm going to recall. Well, you guys can't see it, but I'm just bringing up, or maybe I can allow you guys to quickly just see it really quick. All right. So add window capture. Okay. Which window is that? It's notes. Okay. All right. So these are our notes. And I'm just going to cover my face slightly there. Or better yet, I don't have to do that. I can just minimize this a little bit more. All right. And so let's zoom in a little bit because that's hard to see. Let's look at our answers. So the ones that I think are correct are at the very end of each line. So number one, the answers that were selected were E, C, and B, and I thought it was B, so it was B. Number two is D, and we all agreed on that one. Number three is E. Four is E. 5 is A. 6 is E. 7 is C. 8. 8 is D. Oh man. And I put C. Okay, I want to look back at 8 and see what's up with that one. Number 9 is E and number 10 is B. So if I were taking this test again, I would have gotten 9 out of 10 correct. Which is not too bad. I kind of really wanted to get all 10 correct, but it happens. Honestly, guys, this test, I mean, those were the easy ones. It can really get difficult. I'm pretty sure it gets more difficult as you move on through the test. But yeah, guys. So yeah, good stuff, guys. B for the very last one was definitely correct. Well, in this situation, we're just having fun, right? Pass or fail, we're just having some fun, and we're discussing the science behind it all. Yeah, the ice question got us, right? The answer is, I want to go back and look at it now. The answer is D. I want to see what the solution was for D. Let's see. Right, I want to do this. Let's see. Oh, there's a nice little plot. Yeah, but actually, with some of these problems, when I took the test in number 8, let's quickly actually go over number 8 really before I say that. Oh wait, no. I thought I said 16. T squared, right? I put C. Well, I would have gotten it wrong. If I would have put C, I still would have gotten it wrong. But I thought I said 16. But yeah, when I took this test, guys, my trick to taking the test was to go through all the questions that were just primarily conceptual and required very little calculation. Then I went back and try to attempt to answer some of the more harder questions. The only issue with this test is that for the ones you get wrong, if I'm not mistaken, you're penalized. If you get it wrong, they take away points. Versus just you don't get the points. If you get it right, you get the points. But if you get the question wrong, they take away points on the test. So you really don't want to be guessing. And like I said, luckily I only had to take it once, and I was happy about that. But guys, I had a great time doing this with you guys, and hopefully maybe I might do it again in the future. And hopefully also my iPad will be working when I can actually work through some of the problems. But I hope you guys had fun, and I look forward to our next stream. I do know that Pamela stated that we will not be having our streams next week. So I will not see you next week, unfortunately. But I will be back, I think, the week after. Is that correct, Susie? If you're still here, Susie? Well, I will be back after. I'll be back when all the other streams return as well, including Daily Space. So I will see you guys then. All right, guys. See you in November. All right. Bye.